So in chapter 15, we're going to talk all about oscillations. And oscillations describe how things move back and forth along a straight line or a curve. We have another word, another phrase for this. It's called simple harmonic motion. So this is back and forth motion along a straight line or curve. Simple harmonic motion. We've already studied some examples of this that are simple harmonic in nature that we just didn't realize were. Things like springs and things like pendulums are both examples of simple harmonic motion, and we'll really concentrate on the spring aspects of simple harmonic motion in this chapter. So we can describe an equation, we can write an equation that describes the position of something that's bouncing back and forth along a curve. The easiest equation for describing simple harmonic motion is going to be x, our position, is equal to a times cosine of omega times t. And this is going to give me the position of a bouncing object at any time. A is something called the amplitude. That's how large my bouncing motion is from some rest point. Omega is the angular frequency. This describes kind of how fast you're bouncing. And t is the time that you're interested in. So one of the big advantages of simple harmonic motion is we can visualize it. We can visualize this equation that we have, this x is equal to a times cosine of omega t. And we can define what all these variables are in terms of our graph. So that's all I've done here. I've plotted x on my vertical axis is equal to a times cosine of omega t. And it gives us this curve shape. You could plot this on a graphing calculator, you'd get the exact same shape. My x as a function of t. So this is tracing position as a function of time for a simple harmonic oscillator, for something that's bouncing up and down. I can see what all these variables are. We'll start with a. Where is a on this graph? A is going to be height of your wave, of your oscillator, above the 0 point. Because we need to remember for cosine starts off positive and goes negative. So it oscillates around this 0. The height of that oscillation above 0 is the amplitude. Now another variable of interest related to what we've been studying already is the time that it takes me to go from the top of my wave down to the bottom, back up to the top. So it's that little portion of our wave right there. We start at the top, we go down to the bottom, back up to our starting position where we started from, back up to the same height, that same amplitude. This has a very specific name. The time that it takes to go this distance is capital T, where capital T, as it's been in the past, is the period. And the period, as we already know, is 2 pi divided by the frequency. So that period is the time for one complete cycle of my oscillation. Time for one complete cycle. And this isn't just some abstract equation. This is actually describing motion. This is describing how a spring bounces. So if you look at figure number 15.6, part D in your book, you see that this is actually plotting a spring that's bouncing up and down. So how can I draw that? I can try to draw that on here. We can look at the figure too to make some sense out of this. So I have this spring, and I take it, and I stretch it as much as I possibly can. That stretch, the amount of stretch from its rest position, where it would normally like to be, is my amplitude, is A. I let go of this, and the spring is going to bounce up and down. I'm going to bounce up, and then I'm going to bounce down. And I'm just going to repeat that motion. This bouncing up and down, bouncing up and bouncing down. That is the motion that I'm tracing out here. I bounce up, bounce down, bounce up, and bounce down. That's what this motion, this equation, is trying to describe for us. That's what x equals a cosine omega t actually means. And this is actually a very specific case where I take my motion and I pull it down to our maximum amplitude and let go. But what if I did something in between? How would I describe if I didn't pull my spring to its maximum amplitude? Even without being at a maximum amplitude, pulling my spring as much as I possibly can, my position can still more or less be described similarly. I still have my amplitude that I can stretch my spring, times cosine of omega t. And I'm going to add on this little guy, this little lowercase delta. This delta is called a phase. It shifts where my wave starts. So in the equation we've already seen, in the plot we've already seen, for a cosine omega t, I started at my maximum amplitude and let my wave oscillate. If I don't pull my spring as much as I possibly can, then my wave isn't going to start at exactly the maximum height. It's going to start somewhere a little bit lower, but it's still going to oscillate back and forth. Okay? I still have a cosine wave, so it still starts at its maximum amplitude somewhere. It just doesn't start at this 0 point. So that delta that we have, this phase, describes how shifted I am relative to 0. It describes the distance between where my wave would start at 0 point without the delta and where it starts if I shift my wave, if I don't pull my spring to its maximum stretch. And now we can start to get into some real physics, some real useful, real-world physics. We know our position for an oscillating body, something that's bouncing up and down, for something for a spring maybe. X is equal to a times cosine of omega t. If I want to know the velocity is the derivative of x with respect to time. So I can differentiate this, and I find negative a times omega times sine of omega t by taking the derivative of cosine. Then I can find the acceleration of this spring by taking the second derivative of position with respect to time, which is also just the first derivative of velocity with respect to time. And I take that derivative, and I get negative a omega squared times cosine of omega t. And what I can do is I can plot each of these. I can plot my position, I can plot my velocity, and I can plot my acceleration and see how they all look relative to each other. So how can I visualize these graphs? How can I visualize what's going on? First, we start with x equals a cosine omega t. Cosine starts typically at the maximum amplitude at this maximum a and goes down, crosses 0, reaches its maximum negative amplitude, then goes back up, and then goes back down. So it will oscillate back and forth. That's my cosine function. I'm going to mark some points on this. I'm going to mark the points where I have my maximum values and my 0 point crossings, where I cross the 0 point on my y, on my vertical axis, and then where I reach my maximum point. And I'm going to do that so I can understand how this x position is related to my v position. My v position is the sine of my wave. So the sine and cosine are offset from each other by 90 degrees. So that means where I have a maximum in my position, I actually am crossing 0 for my velocity. So maximum in position is a 0 for velocity. So let me mark all those kinds of little turning points. Maximum in position is 0 in velocity. Maximum in position is 0 in velocity. Maximum in position is 0 in velocity. And then I have these 0 points where my position is at a 0. At these points, when I have a 0 in position, I have a maximum in acceleration, or in velocity. So when I have a 0 in position, I have a maximum velocity. 0 in position is maximum in velocity. So what I'm going to do now is draw my sine wave. And I picked my little 0 points to go negative initially because of this negative for my velocity. If you can plot this on your graphing calculator, and it'll show you exactly what I'm plotting here. The sine goes negative, goes positive, reaches a max, and then goes negative. So my waves are offset by 90 degrees from each other. My position is cosine, my velocity is sine. And finally, if I want to do the acceleration is going to be the same phase. It's not going to be offset at all from the position. It's very well related to position because they're both cosine. They both involve having that cosine, except my acceleration has this negative. So this negative means instead of starting up top with a positive amplitude, I start down low. I start with a negative. And then I'll have the same exact shape, same exact crossing points as my position. I'm just kind of a mirror image of my position. So I have my position is x in green, my velocity is offset by 90 degrees in red, and my acceleration is pretty much the same phase, the same positions as my cosine, but it's negative. So it's flipped, it's a mirror image. What does this all mean in terms of springs? How is this showing us what springs are doing? To understand this, we need to keep in mind this point. It's a very important point. That a maximum position equals a 0 velocity. And a maximum negative acceleration. And conversely, a 0 point in position is equal to a maximum velocity and a 0 acceleration. So what does that look like, and how in the world does this explain a spring? So let's analyze it in terms of a spring actually bouncing up and down. Let's say I have my spring and my mass hanging from the end of it. I pull it up a little bit to offset it. The offset that I apply, however much I pull it, that's going to be the amplitude. That's how far away from its rest point I am. In terms of springs, when we've actually talked about them, this amplitude is usually that x for the Hooke's law force if F is equal to kx. So I offset it by some amplitude. And then I let go of it, and it bounces down. It reaches some point where its position is 0. That 0 position is again where its rest position would be. At this point, if we remember the calculations we've done before regarding this kind of situation, at this point where I'm at my rest position, my position is 0. X in terms of our equation x equals a times cosine of omega t is equal to 0 at this point. But according to our findings from before, the velocity should be equal to a maximum. And if you remember, that was the case for when we were studying the spring force, for when we were studying Hooke's law forces. If you don't remember this, go back to your notes. It is in there, I guarantee it. And then as we keep bouncing, we reach some maximum distance, negative distance, away from our rest position, away from where we started from. At this point, my spring is going to turn around. At that exact instant, when my spring turns around, the total velocity that I have is equal to 0, because I'm switching from going down on one side to bouncing back up on the opposite side. So at this point, my velocity is equal to 0, but my acceleration is equal to a maximum, because I have the maximum amount of stretch. So my force that's pulling me back up, this force that's restoring me back to where I want to be, back to the natural position of the spring, this force is at a maximum. If your force is at a maximum, then your acceleration is at a maximum. So everything we've just read, everything we've just studied, all makes sense, and it all makes sense in terms of things that we learned about back in the force chapters. And one final kind of cool thing to make note of is our position equation and how it's related to our acceleration. X equals a times cosine of omega t. We're not going to really worry about phases too much in this class. So we'll, as long as we know what that delta is, we won't worry too much about that. So if I want the acceleration of this is the second derivative of the position with respect to time. So I can find that second derivative. We've already found it is negative a times omega squared times cosine of omega t. What I'm going to do is shuffle this around a little bit. I'm going to shuffle this around so that my acceleration is just moving where I'm writing things is equal to negative omega squared times a cosine of omega t. So all I did was switch the order that I wrote the omega and the a. I just flipped those. And if I look at this, a cosine of omega t is equal to x. So my acceleration is just equal to negative omega squared times my position. What this tells us is that my acceleration is proportional to my displacement. But it's opposite in direction. And this applies for simple harmonic motion. And this should kind of make sense, because we know from Hooke's law, we know from restoring forces, we know from spring forces, that the acceleration was negative, because the force is equal to negative k times the position. This Hooke's law force, this spring force, it describes the force on a simple harmonic oscillator. So all this information that we're finding with this new equation, this simple harmonic equation, a cosine omega t, isn't really new. It's just repeating things that we've already learned, Hooke's law, the restoring force, and it's restating them in terms of a new type of equation that we can just do a little bit more complicated problems and situations with. And here's where we really get into that, with section 15.2, which is all about this simple harmonic oscillator, SHO. Now, to describe anything that's moving, we need to know about relevant forces. And these relevant forces are described by something we call an equation of motion. And customarily in physics, the equation of motion that we use is describing forces. And for forces, for springs, we have Hooke's law, F equals negative kx. We also have Newton's law, F is equal to mass times acceleration. So we have Hooke's law, and we have Newton's second law. These are equivalent laws. They say the same thing. So we can come to our oscillator approach and get our force is equal to mass times the acceleration, which is the second derivative of x with respect to time. So I can shuffle this around and set equation number 1 equal to equation number 3. So I find mass times d2x dt squared is equal to negative k times x. Okay, and now I'm going to play with this. I'm going to fiddle with this a little bit. My acceleration, which we just found on the previous slide, is equal to negative x times omega squared. So I'm going to plug that in for my d2x. So on one side I have mass times my acceleration for my oscillator is equal to negative k times x, is equal to my Hooke's law. I can see here that I can cancel out my negatives, so my two negatives cancel each other out, and my x's cancel each other out. And I'm going to find that mass times omega squared is equal to k. So omega squared, the frequency that I'm bouncing at, how fast my spring is bouncing, is equal to k divided by m, and I can take the square root of both sides to find that the frequency, how fast the spring bounces, is equal to the square root of the spring constant divided by the mass that's bouncing. This is the frequency of a bouncing spring. So if I take this and I plug this into my equation for position of a harmonic oscillator, my position x is equal to a times cosine of omega times t, where omega is square root of k over m, times the time, plus a delta. For the most general equation for a harmonic oscillator describing a spring. Now, why do we bother to write omega in terms of k and m? This is very useful because omega can be hard to find. It can be hard to know what that is. It can be difficult to measure because it changes with time. But the omega can be determined if I know my spring constant, how stiff my spring is, and the mass that I'm hanging off of that spring. So this omega can be independently determined very easily to perform experiments. To get some practice with this, with these kinds of ideas, I suggest looking at the following checkups. Do checkup 15.2.2 and 15.2.3. So the final thing that I'll hold us responsible for in this chapter is figuring out energy of a simple harmonic oscillator. We know already that energy is equal to kinetic energy plus any potential energy we can have. And kinetic energy is 1/2 mass times velocity squared, and potential energy is equal to 1/2 k times x squared. I can write this in terms of my oscillator as 1/2 mass times an equation for my velocity, which we found before was negative a times omega times sine of omega t, and that's got to be squared for my velocity, plus 1/2 k times x squared, where x is a times cosine of omega t squared. So I can multiply this out, and I'm going to find that my energy, E, is equal to 1/2 mass times a squared, omega squared, sine squared of omega t. That just comes from squaring this velocity. And I'm going to add on my 1/2, my k, times an a squared cosine squared omega t. And this comes from squaring my x. So now I have a new equation, and I need to shuffle things around. I want to shuffle things a little bit to make things a little more obvious. 1/2 my mass times omega squared times a squared times sine squared of omega t. So all I did here was switch the positions of where I was writing my a and omega. I just flipped these around. Okay, and then I have plus 1/2 k times a squared times cosine squared of omega t. And we're going to continue this on the next screen. I have my energy equation, this previous equation that we just found, that we've been deriving all along in the previous slide. I look at this m times omega squared, and I remember that omega squared was equal to k divided by m. So if I shuffle this around and solve for k, I now can see that m omega squared is just equal to k, is equal to my spring constant. So I can plug that in for my spring constant. I can plug it in for my m omega squared and get that E is equal to 1/2 times k times a squared times sine squared of omega t plus 1/2 k times a squared times cosine squared of omega t. And what I'm going to do is factor out the common factor that I have in here. I have a 1/2 ka squared that's in common between both of my pieces of my addition, pieces of my sum. So I factor that out, and I end up with sine squared omega t plus cosine squared omega t. It's the same thing as we have above. I just took out a 1/2 ka squared. And if we know trigonometry tells us that sine squared omega t plus cosine squared is equal to 1. This is something we call a trig ID, a trig identity. They're very useful. That's a very useful one to know, so I would memorize that. So if that's equal to 1, then the energy inside of a simple harmonic oscillator is equal to 1/2 k times a squared. So the total energy I can get out of a spring depends on the spring constant and the amplitude, or how far I can stretch that spring. And if you think about this conceptually, it should make a good bit of sense to you.